How do you teach a computer to do something without writing out the rules? Instead of writing rules, you show it examples, thousands of them. With a little bit of math, patterns are identified and fitting rules created. And that's the entire idea behind supervised learning, central to powerful systems like ChatGPT and Midjourney. In this video, we'll break down what supervised learning actually means, how it splits into the two main types, classification and regression, and what the key ingredients are that make learning possible in the first place. Let's get into it. So what is supervised learning? Well, the term consists of two words, supervised and learning. Let's start with the learning part and look at our example. Here, we're trying to determine, based on a picture, whether we have a cat or a dog in the picture. Now, if you tried to write a computer algorithm by hand that does this, you would either not get a very good program or spend a lot of time creating it. It's not very clear how to detect a cat. We as humans may be able to see a picture and know that is a cat, but we can't say what our decision is step by step. Since this picture is high dimensional, let's say in this case we have 1,000 pixels on the X and Y dimension, this would give us a total of 1 million pixels. And how do we say how to act for each pixel to decide whether this is a cat or a dog? Well, it's not very clear, and that's why we don't write algorithms for this sort of task by hand. This is what we use learning for. Computers can learn from data rather than following handwritten rules, as in classical computer programming. They find patterns on their own. So what we do is provide examples, and from these examples, a model is learned. So this model is just a set of rules that is followed to make a computation. The other word, supervised, gives us an indication as to how our data looks. So what our examples are like. The supervised term means that data comes with answers attached. For every input in our data, we also have the correct output. So for this picture of a cat, we are given that this is a cat. So when we give this example to the computer, it knows that it is expected to give us the output cat. And the same for this picture of a dog. And these correct outputs are called labels. So supervised learning is learning that we do on data that has labels. In essence, in supervised learning, we are given examples of inputs and outputs. So we are given an X and a Y, and we are trying to learn an F, which entering our X gives us our Y. So we're trying to learn the function, or rather the mapping, that is given by our data. Now, there are two types of supervised learning, namely classification and regression, as I've mentioned earlier. And the difference here is the type of data we have, specifically what our expected output is. Classification is corresponding to the example we had before, where from our inputs, we want to derive a class. So that's what classification comes from. And in our case, the two classes are cat and dog. In this example, our input is an image, but for classification, this can be pretty much anything. So usually this would be some sort of vector, and the output would then be a discrete class. Usually it's written like this, that our y comes from a set of c different values. Now in our case, I wrote the string cat and dog, and this is simply for us to know what it means. But in the computer, we would store this as two different values. For example, 1 for cat and 2 for dog. So what we actually want our model, so our function that we're learning to do, is when we're given an image x, if that image x is a cat, we want f of x to then be 1. So what encodes the class cat. And for an image of a dog, we would like this to be 2. The main part of classification is just that our output isn't continuous. So what we are predicting based on our input x is a finite class. So what our image or our inputs corresponds to, what class it corresponds to. In contrast, in regression, the label is just a number. So in our case, we have an input vector of size 2 and an output value, which is just a scalar. Let us say that we're trying to predict what the rent price of an apartment is based on its size in square meters and the number of rooms. And then this would be the predicted price in euros. In this case, we don't want our output to be discrete and finite, since rent prices are continuous. So the range of prices is not restricted to whole numbers. It's not restricted to values between 10 and 2000. So the label is no longer a class, but it is a number. So we can also see this y is now continuous. So it's in the real numbers. And I've written it as a vector because, sure, in our case, we're only predicting the rent price, but we can also predict several values at once. There's nothing stopping us from, for example, calculating a vector which gives us both the price and the estimated number of bathrooms, for example. So the important difference between classification and regression is that in regression, this output is continuous, and in classification, it's discrete. So in classification, our output corresponds to a class, and in regression, it is just a number that we're predicting. And this different kind of data also requires slightly altered algorithms, but we'll get to that in a minute. We've seen what our data looks like, but I haven't told you anything about our model, the actual thing we're trying to get to make predictions, or even how we get it. So there are actually a couple of things that are hidden by this arrow here. So how we get from our data to the actual model, which then is learned from this data. So the 3 ingredients that make learning possible. The first of the 3 ingredients that enable learning is the model. So it's our function f, based on which, using our input x, we compute a prediction. And I added theta here to show that this is a parameterized model. What this means is that our model, or our function, computes its output based on a recipe that is dependent on theta. So these are its internal knobs that can be tuned and that need to be tuned. So since we are learning from our data, we need to have some place where we can store our learned information so that we can make a prediction based on this. A very simple example would be the function f theta, where when we have our input x, we compute theta transposed times x to get our output. So this is assuming that theta is a vector of the size n, and our input x is also a vector of the size n. Then our output, y, will be a single value because of this product here. So for example, x can now be our vector of the size 2 in our regression problem. That would have been the apartment size and number of rooms. And theta would now be 2 values, theta 1 and theta 2. So what we get here is theta 1 times x1 plus theta 2 times x2. And our output would then be a linear combination of our input. And that would be our prediction. Now, this would be a simple linear model and probably not sufficient to model our prices of apartments, but this is just a toy example trying to show that our function f is dependent on these parameters, which we can tune. Now, our second major component is the loss function. Since we are learning, we want to tell our model how good it is doing. So it tells us how wrong our prediction was. And using this, our model then tries to minimize this. So it tries to improve its prediction. Now, what I noted here with y hat is our prediction that we make. So exactly our function applied to this input. And what I wrote here without the hat, the y itself, is the true label. So this is what we expect as an output. And what our loss function now tells us, which is here denoted with L, is how well does y and y hat correspond to each other. And this, for example, can be the measure of how far apart these two values are. So for example, taking the difference of both of these values and then computing the square. Now, why would we use a square here? There's several reasons, but one of them is we want to be indifferent to whether y is larger to y hat or y hat larger than y. So it's just supposed to make this value always non-negative. So in our case, if we predicted the price 800, but the actual value is 600, this would be 600 minus 800 to the power of 2, which is 200 to the power of 2. And that is a measure of how wrong we were. If we were to have a perfect prediction, or say one that is off by 1, so 700 and say 701, the difference would be 1, so our error would be 1 squared. And this is also just another word. The loss is sometimes also called the error. It is just a measure of how much of a mistake our model made. The last ingredient of our supervised learning is the optimization. We've seen now how much of an error or how much of a mistake we did with one prediction. And we now care about minimizing this. So we want our model to be as good as possible, which means getting its error as close to 0 as possible, at least in this case here. Depending on how you find this loss, 0 might not be reachable or values underneath it might be possible. Either way, we try to minimize the error. This is exactly what this formula here shows. The minimization of this loss function with regards to theta, where theta were our model's parameters. Since these are the things that we can actually change. So this is what we want to minimize over. I've written this simply using the minimization, but what is behind this is actually certain algorithms to do this optimization. So the actual process of adjusting the knobs to reduce the loss. This is its own topic for a future video. Now, I am not mentioning some of the more specific either optimization or regularization concepts, as I think they are secondary to these three main components, which are fundamental to every supervised learning problem and also provides the most difference between models or between systems. So these three aspects offer different knobs in the entire system, meaning based on which model you choose, you get another prediction. Based on which loss function you use, you optimize the model differently. And based on which optimization system or process you use, you might reach optimal losses or not. These are all aspects that can be changed depending on your problem. And this is what differs all these different machine learning models from each other. One thing which I did not note here yet is that what we actually do, so I wrote down the minimization of the loss for one prediction, but what we usually do is do this over all of our data. So the way this minimization would actually look is that we minimize over the mean of all of our data points, so saying we have n different data points, and we do the mean of their losses, where we take yi, this is the label of our data point I, and the output of our model given the input xi. So I wrote this before as just a shorthand notation with the y hat and did not add the subscript I, but adding the subscript I now just corresponds to our data. So how we usually write our data is d with the tuples, so collection of two values, the input and the output, and we have n many of them. So this is what the subscript corresponds to. And this is then usually what we try to optimize. And if we use exactly this error function here, this would be the error function here, and in total this would be called the mean squared error, also written as MSE, which is a common simple function to be optimized. So this would be one formulation which summarizes our model, loss function, and optimization formula in one formula. And then you could plug in this model description here to define us having a simple linear model as I've described earlier. If any of the math in this series ever feels unfamiliar, like vectors, dot products, or any of my notation, my linear algebra playlist covers all of it, so check it out here. As for what to watch next, I'll let YouTube decide based on what it learned from your data. Let me know what topics in machine learning you'd like to learn more about in the future. And as always, thank you for watching.